Hey guys, what's up? Welcome back to our video series on equilibrium existence proofs. So in this video, we're going to go and talk about proving equilibrium in the context of a production economy. So this is the theorem that we have down right here. So we're going to suppose that u of h as a function of x of h, where h goes from 1 to capital H, is strictly quasi-concave over our commodity space denoted by x of h, which is defined by a n-dimensional real number space, or a really positive real number space, and consumer h, right, let me just go fix that up real quick, has an endowment omega h within our commodity space. Suppose also that our production sets denoted by y of f, right, where f goes from 1 to capital F, are closed and bounded from above, and that 0 is within our production sets. Then there exists a Walrasian equilibrium. So the way that we go and we prove this, right, is that we're going to follow really the same steps. So our first step is that we're going to normalize our prices, right? Step number 2 is that we're going to define a mapping. Then we're going to use Brouwer's fixed point theorem, and then we're going to go and use Walras's law to bring everything together. So step number 1 is that we're going to normalize our space of prices, right? This is going to be known as our price simplex, right? Where it's our vector of prices such that our prices are in our n-dimensional real number space, or a positive real number space, and that the sum of all these prices sum up to 1. Step number 2 is that we're going to define a mapping G, which goes and maps our price simplex to itself. From there, we're going to go and take G of P, and we're going to go and write it as follows. So the main trick here is that we're picking a mapping, right? We're able to go and do this because we want to know, is there a mapping that exists over this space here, right? Where this Z plus here is this special type of excess demand function where it only spits out a positive number there, right? Where excess demand is positive. We're going to note that our excess demand, or our total excess demand here, is going to be the summation over all households' demands, right? As a function of the prices and this term here, right, which is the value that they hold, right, that being the value of their endowment and the shares that they hold in each one of these firms, and also that's going to be minus their sum total of all the endowments and the production plans that we go and we have down here. Just forgot to put a little j there. Step number 3 is that we're going to appeal to Brouwer's fixed point theorem. Since G of P is a continuous function on the closed and bounded domain of our price simplex, we're going to say that there exists a price vector, right, P bar, such that if we put in this price vector into our mapping, it's going to spit out this price vector. Now, the next thing that we're going to do is that we're going to consider a particular mapping here in our vector of prices, right? So we have a what we call a set of price functionals, right? This is a price functional because it's a vector of functions, right? It's a function of G of P bar. Right, let's go put B bar here. Forgot to put a little bar there. G2 of P bar. And we're just picking one of those down there. Rearranging from the previous equation, that's just cross multiplying and subtracting Pj from both sides. Over here in this step, we get the following result. Next, we're going to go and start doing some manipulation where we go and we multiply both sides by Z of j. From there, we're going to then go and run a summation operator over all j in our set. Now, this is where we sub in our secret step 4, right? What was step 4? Remember, that's just Walras's law, right? That means this is going to be equal to 0 for every p, right? I shouldn't put a p bar there, right? It's just going to be for every p there. So we can say with confidence that this is equal to 0. And once we get down to this result down here, we have completed our proof. Why is that? Because zj plus, right? This can't be something that's positive, right? This can't be positive because that would violate Walras's law here and would violate the quality that we have set up here. So we go and we prove that there indeed does exist an equilibrium because we're just going essentially from all of this stuff and showing that z of p right here is going to be less than or equal to 0, or in this case, we have a strict binding definition here where z of p is just equal to 0. So this is our third example that we have in our series on equilibrium existence proofs. I want to go and go more into depth on this idea, right? About it seems to be that no matter how we go and we define our excess demand function or our environment, as long as we can play this game with our excess demand function, we seem to be able to prove an equilibrium goes and exists. So what requirements do we need here? Is there anything that we're not speaking about out loud? So we're going to go through a theorem, right, in a future video called the Sonnenschein-Mantel-Dubrow theorem, which goes and says you don't need a lot to go improve equilibrium existence. And we're going to talk about what that means. So I hope to see you in that video. Take care.